Hello everyone. Once again, we are going to solve an AB free response situation in full. This time, we are going to focus on a one-dimensional kinematics problem so that we can study the position, displacement, velocity, and acceleration of a certain object moving up and down a ramp. Of course, we have to deal a little bit on forces because that's the only way to know what's happening with the acceleration. So without further ado, let's see what the problem gives us. A block of mass m is projected up from the bottom of an inclined ramp with an initial velocity of magnitude v0. The ramp has negligible friction and makes an angle theta with the horizontal. A motion sensor aimed down the ramp is mounted at the top of the incline so that the positive direction is down the ramp. The block starts at distance d from the motion sensor as shown above. The block slides partway up the ramp, stops before reaching the sensor, and then slides back down. There are several key points to study here, but one of the most important is that it says that the positive direction is down the ramp. This is important because if we are saying that this is the positive direction, then the initial position has to have a positive sign, d, but the initial velocity is in the negative direction. So if you want to talk about the velocity, you shouldn't just say v0. That's only the magnitude or speed. The velocity should be negative v0 to take into consideration the direction. Now, consider the motion of the block at some time t after it has been projected up the ramp. Express your answers in terms of mass m, position d, initial speed v0, time t, and angle theta and physical constants as appropriate. So now they want you to determine the acceleration a of the block. In order to do that, we have to think about the forces. And the best way to consider forces is by considering a free body diagram so that you can see what's going on with each of the forces acting on this block. Now, they also told you that the ramp has negligible friction, and so there are only two forces acting on this block really. One of them is the gravitational force, mg, and you will recall from previous discussions that the angle that the ramp has with the horizontal is the same angle between the gravitational force or weight and the y-axis. Also, there is the normal force, which is perpendicular to the ramp, and therefore it is along the y-axis. But if it's perpendicular to the ramp, it has no component in the direction that the block is accelerating. Therefore, the only thing that is accelerating this block is the x component of the weight or gravitational acceleration. By taking Newton's second law, we have that the net force along the x-axis is equal to mass times acceleration, and the only force acting there is the x component, which is mg sine of theta, because the angle is opposite to that component, and so of course masses cancel out, and the acceleration is equal to the constant value g sine of theta, and that is the answer that we are looking for. Next, they want you to determine an expression for the velocity v of the block. Now, this can be done by memory. You can very well remember that a final velocity is equal to an initial velocity plus acceleration times time. But it is also true that you can do this from calculus by considering that really the velocity, when you derive it, gives you the acceleration. So the acceleration is nothing else than the time derivative of velocity. Therefore, dv dt is equal to g sine of theta, which is a constant, as you remember. So the differential of velocity is equal to g sine of theta times the differential of time. From there, it's a simple step to just take the integral over an interval from 0 to a certain time t. And now, in that interval, you go from the initial velocity. Now remember that the initial velocity has to have a negative sign because it's going up the ramp. Negative v naught to some time-dependent velocity v. Therefore, when you integrate, the integral of 1 is just the variable on the left-hand side, that is v, from negative v naught to some variable v. And on the right-hand side, the integral of a constant is the constant times the variable, which in this case is t, and you evaluate that from 0 to t. Now, this means that on the left-hand side, you get v as a function of time minus negative v naught, and that's equal to g sine of theta times t minus 0, because 0 times the constant is 0. A little algebra, and what you get is that your velocity as a function of time is equal to negative v naught plus g sine of theta times the time. You will recall that this is a linear function and you have a negative y-intercept, negative v naught, and a constant slope, which is the acceleration g sine of theta. Next, they want you to determine an expression for the position x of the block. Once again, you can do this from memory. Remember that the displacement, which is final position minus initial position, is equal to initial velocity times time plus 1/2 acceleration times squared. But as always, it is a lot more fun to do this from basic principles, which in this case is integral calculus. The velocity is nothing other than the time derivative of position. So dx dt is equal to initial velocity time. Initial velocity actually has a known value, which is negative v naught. And also, this is given by negative v naught plus g sine of theta times t. Therefore, the differential of position is equal to negative v naught plus g sine of theta t dt. Once again, from there, you have to integrate over an interval from time 0 to some later time t. And now, what is the position at time 0? Well, that's just d. And the position at some later time is some later position x. When you integrate on the left-hand side, you get the variable from d to x. And on the right-hand side, once again, a constant integrates to a linear function, minus v naught times t, and the integral of t is t squared over 2. So this is 1/2 g sine of theta t squared, evaluated from 0 to t. So this is x minus d is equal to negative v naught t plus 1/2 g sine of theta t squared. If you solve this as a function of time, then the position in terms of the time is given as the initial position plus initial velocity times time plus 1/2 of the acceleration times time squared. And that is the expression that we were looking for. Next, they ask you to derive an expression for the position x min of the block when it is closest to the motion sensor. Express your answers in terms of the same variables as before: mass, initial position, initial speed, time, theta, and physical constants as appropriate. Now, if you consider your intuition about the motion of this block, Remember that it's going to move with an initial high velocity, and then it's going to come to a rest position, and then it's going to come back down to get a final velocity in the positive direction. So this means basically that if this is the minimum position that it's going to get from zero, obviously the speed there is zero. So there is your key point there. Your final velocity must be zero. Now remember that your initial velocity is negative v naught, and above you just got the acceleration, which is positive g sine of theta. Now the displacement for this situation has to be the final position x min, which is what you are looking for, minus the initial position d. There is a kinematics equation for this. You have that the final speed squared is equal to the initial speed squared plus 2 times the acceleration times the displacement. And in this situation, you get 0 is equal to v naught squared. Remember that if you square it, the sign goes away, plus 2g sine of theta times x min, which is what you want, careful, minus d. So now we only have to kind of manipulate this equation to get x min. You have that negative v naught squared divided by 2g sine of theta is equal to x min minus d. So the minimum position x min from the origin is equal to d minus v naught squared divided by 2g sine of theta. And that is the answer that we were looking for. Now, the next part is more conceptual than anything else. On the axes provided below, sketch graphs of position x, velocity v, and acceleration a as functions of time t for the motion of the block while it goes up and back down the ramp. Explicitly label any intercepts, asymptotes, maxima, or minima with numerical values or algebraic expressions as appropriate. Now, let's start with position, which is one of the simplest things that we have here. The initial position was d and it was positive, so you know that you should start over here. Also, it starts moving in the negative direction, so this graph should actually be going down, but it doesn't reach zero. Therefore, if there is an acceleration, your position should have a parabolic shape like this, where this position is actually the minimum position that we found above x min. Now we can actually look at this in a dynamic way by considering this graph. Look at how, as time goes by, the graph starts at positive d, moves downwards until it gets to the minimum position, and then it moves upward. What is the physical meaning of this? In the first part, the block is moving up the ramp, getting closer to zero. In the second part, it is moving down the ramp, going in the positive direction, so that's moving actually away from zero. And so that's your position equation. Next, what is going on with the velocity? Well, remember that your initial velocity is negative, so you should start below zero actually. It's negative v naught, and you have a constant acceleration. The acceleration is the slope of the velocity, so you should have a constant slope, which basically means a straight line. It stands within reason that if the force is constant and the acceleration is constant all throughout, then you're going to start with the same speed when you go all the way back down. And that means that your velocity is just going to be the opposite. And this looks dynamically this way. Notice that you start out negative, get to a position where the speed is 0, and then end up with a positive value equal to the initial negative value except in sign. So in the first part of this, the object is moving up the ramp, decreasing the speed to 0, and then it's moving down the ramp, increasing the speed to the same speed that it started with. So that is your graph for changes in velocity. Finally, you want to talk about acceleration. And in this case, your acceleration, as we said before, is a constant value, and it just happens to be positive. Positive g sine of theta. Any constant function is a horizontal straight line, and so your acceleration should actually look like this. Starts out with one value and it continues with that value throughout the whole trip. So those are the graphs that we have for all the different quantities. And now they want to discuss something a little after the object moved down the ramp. After the block slides back down and leaves the bottom of the ramp, it slides on a horizontal surface with a coefficient of friction given by mu k. Derive an expression for the distance the block slides before stopping. Express your answer in terms of mass, initial position, initial speed, theta, mu k, and physical constants as appropriate. Now remember that this term, as appropriate, basically means whenever you need to use a variable. You don't always have to use a variable. But the point is that this block at the beginning has a speed in the positive direction of v naught, and then it eventually comes to a stop. So your final speed is 0. The only way that that happens is that the acceleration is in the opposite direction. Therefore, it's a very good idea to consider what's happening with the forces in this case. For this block, you have a gravitational force mg directly down. Now you're on a level surface, so your normal force is directly up, and since there is no acceleration in the vertical axis, these two have the same magnitude. On the other hand, you have a frictional force, because they mentioned the coefficient of friction mu k, which is the only one acting on the x-axis. So using Newton's second law, what we get is that the net force is equal to mass times acceleration, but the friction force is going in the negative direction, so you get negative friction is equal to mass times acceleration. Negative mu k times the normal force is mass times acceleration, but the normal force is equal to the weight, so negative mu k times mg is equal to mass times acceleration. Once again, masses cancel out, and your acceleration is equal to negative mu k g. Add that to the fact that the initial velocity is v naught, and the final velocity is 0, and what you want is the distance the block slides, or in other words, they are asking for the displacement. Now you have an equation for this from kinematics. We already used it. Its final speed squared is equal to the initial speed squared plus twice the acceleration times the displacement. Final speed is 0. Initial speed is v naught squared. Acceleration is mu k times g, but it is negative, and so what you have is a negative divided by another negative, so this is positive v naught squared over 2 mu k g, and that is the answer that we were looking for. The final question here is about a what-if situation. What if in this situation there is actually friction up the ramp? Suppose the ramp now has friction. The same block is projected up with the same initial speed v0 and comes back down the ramp. On the axis provided below, sketch a graph of the velocity v as a function of time t for the motion of the block while it goes up and back down the ramp, arriving at the bottom of the ramp at time tf. Explicitly label any intercepts, asymptotes, maxima, or minima with numerical values or algebraic expressions as appropriate. Now, if we want to analyze what's happening with the velocity, we need to consider the acceleration, which now we have no reason to think it is the same going up and going down. The reason for that is that if you look at the forces, the direction of the forces is not the same because now we have an extra force acting here. We have friction, and so there is the gravitational force, which is giving us a component down the ramp, mg sine of theta. There is a normal force, which cancels the y component of the weight. And when the block is moving up, the friction force is going down the ramp against the motion. So in that case, the net force is the sum of the x component of the weight and the friction force. But what happens when the block is moving down? If the block is moving down, then you have the x component of the weight going down, and you have the normal force, which is doing nothing in the acceleration direction. And if it's moving down, the friction force is going up against the motion. Therefore, your net force is actually the difference between the x component of the weight and the friction. Therefore, your acceleration on the way up needs to be higher than your acceleration on the way down. And that means that the slope of your velocity graph is different when you're going down than when you're going up. When you're going up, you start with negative v0 as usual, but you need to go steeper because you have a higher acceleration. And it also makes sense that if you have greater acceleration, it's going to take less to go all the way up than it's going to take to go all the way down. Therefore, your speed after reaching the highest point increases more slowly, and it doesn't quite get to v0. Your final speed should be less than v0 because you don't have the opportunity to reach the same final velocity. So, not only you have a higher acceleration, which means a greater slope, you also reach the highest point before half the time, and you don't get to the same speed when you go back down. So, I hope this analysis becomes useful for you, and thank you for your attention, and I'll see you next week.